Hello, everybody. I'm Carmine from Dompe Farmaceutici, and I am the computer-aided drug design coordinator in the Exscalate4COV project. I'm a computational chemist. Today, we will take a look to the analysis of the main protease of coronavirus that we carried out by using a molecular dynamics simulation. We focused our attention on the monomeric and dimeric form, the functional one of the 3-TL protease.
What were some of the things that you were hoping to see by using an MD simulation?
We are focusing on the apoform of the proteins. Thanks to molecular dynamics simulation, we want to explore the behavior of the proteins in order to then go through the virtual screening simulation by using the target and the protein in a dynamic point of view. With these methods, we can explore a huge conformational space that can give us more than just one X-ray structure. We generate these files by using Romax 2020 and Amber 99 force field, and we generate 20,000 frames for each microsecond of simulation. So as you can see here, we are evaluating the distance between the catalytic diet that is composed by cysteine 145 and histidine 41. And to do this, we have to produce an apoform of the protein because the X-ray of the starting structure, the 6LU7, is combined with a covalent inhibitor. So we split the ligand to monitor the distance and the behavior.
If you step through them one by one, you can actually see the surface movement here.
Yes, these loops can give a specific shape to the binding site that allow or not the ligand to access catalytic diet.
We have the distance between these two residues that, if they're separated too much, then it's not enzymatically active anymore, which is what happens in the monomeric state. And therefore, that's why we think this enzyme, it only works when it's dimerized. The distance between cysteine and histidine, so it goes up to 4 angstroms sometimes. So that's going to disrupt the interaction between the catalytic diet, making not possible the enzymatic activity anymore. Yeah, so these two alanines here seem to play a role as well in the, keeping the dimers together, which has, of course, a role in the enzymatic activity.
Yes, this is true, and this is a very important anchoring point for the dimeric structures.
It's interesting how just one of the monomers at the time is active, right? So if this one's active, it appears to be inactivating this one here. And there's some things suggesting that this might be alternating between one monomer and the other.
Yes, exactly. And we go in depth to understand this behavior. Also in the SARS-CoV-1 proteases, it seems to be the same behavior.
Yeah, and regarding those anchoring points, if I remember correctly, there were threonines in the SARS-CoV-1, which brings a lower attraction. So the SARS-CoV-2 gets tighter. The two monomers, they interact stronger and therefore has more enzymatic activity, which is good for the virus, not good for us, right?
Exactly. So, for example, we had some issues regarding this tightness when we go through the docking studies, because if the binding pocket and all this region is so tight, it became difficult to dock.
This inhibitor here is this peptomimetic N3 inhibitor, which has a covalent bonding over here in the cysteine 145.
If you take a look, some interaction are conserved. Some of these ligands don't care about the cysteine 145 because interacts with other important residues. In the case of the non-covalent binders, these are the region in which some of the H-bond interaction are maintained.
Yeah, here we can see clearly how the flexible loop is clearly interacting. So I'm assuming that if it stays away, as it moves, as we saw in the simulation, it'll disrupt this interaction here. And probably that one up there too, right?
Yeah. Yes, in this case, the ligand is able to maintain straight the blue region with the green one and block the enzyme in this conformation that is useless for the virus. As you can see here, this is the ligand, the 3WL, that interact exactly in the same binding pocket of the covalent ligand, but without any interaction with the cysteine free from
Correct.
the interaction regions. From this part of the protein on this loop, the loop that contains the methionine 49, there is a hydrophobic region that can interact with the hydrophobic core of the molecule. I think that by using this virtual reality, combining with other powerful tools such as molecular dynamic simulation, we can obtain better results. I'm so curious to analyze this structure that we produced using VR technologies.
What does collaboration look like with the other members of the Exscalate4COV consortium? Because I know you guys are spread out all throughout Europe.
We are working with Swiss bioinformatics group that carried out the homology model prediction in the first steps of this project. And of course, the data that come from the computational part is then in a very quick way shared with the guys that is carrying out the biological evaluation.
Thank you so much for sharing these files with us and for all the efforts you're doing against COVID-19. Nanome's really looking forward to further collaborating with you and the rest of the Exscalate4COV consortium.
Thank you guys.